Hi everyone, welcome to Go Classes. In this lecture, we will study DMA, that is direct memory access. So this concept DMA we use for data transfer between IO device and main memory. Okay, see what is this DMA? Let's see the definition. DMA, this is a mechanism. Remember, the name itself is telling you what this means. Direct memory access means the IO device can directly send the data to the main memory, or basically between IO device and main memory, we can directly send the data, okay, without any involvement of the CPU. Okay, so this is the idea that DMA, this is a mechanism, direct memory access. This is a mechanism which we can use for data transfer between IO device and main memory without much involvement of the CPU. So CPU will be, I can say, very less involved during this DMA data transfer. Okay, so let me tell you this DMA. This DMA is used for data transfer, as I told you. DMA, direct memory access. This mechanism we use for data transfer from IO device to main memory, from main memory to IO device, or from memory to memory. Okay, so we can use this DMA. Remember, this direct memory access, this mechanism we can use if you want to, if you want to transfer a data from memory to memory, like in the main memory, from one location to another location. If you want to transfer the data, then also you can use the this DMA, this direct memory access. This mechanism you can use. Okay, so the concept is actually very simple. Direct memory access means without much involvement of the CPU, we can directly transfer the data between IO device and main memory. Okay. Now, in the previous lectures, we have already seen how to transfer data between IO device and main memory. So we have seen different techniques. Like we have seen what is programmed IO, or I can say program controlled IO. Another is interrupt driven IO. Another is direct memory access. In this lecture, we will study direct memory access, but in the previous lecture, we have already seen this programmed IO and interrupt driven IO. Okay, so you can see in the previous lectures, you can see here on the YouTube, you can find these previous lectures where we have seen what is this programmed IO, we have seen what is this interrupt driven IO, we have seen interrupt, we have seen interrupt processing, okay, nested interrupt, basically all the concepts related to interrupt and programmed IO. These concepts we have already seen in the previous lectures. Now you might be thinking, sir, if we already have programmed IO and interrupt driven IO, these two mechanism, these two data transfer techniques we already have, then why we need a new data transfer technique, that is direct memory access? Okay, so this is what you might be thinking, that sir, what is the difference between programmed IO, interrupt driven IO, these data transfer techniques which we have already seen in the previous lectures? What is the difference between these techniques and this DMA? Okay, so let me tell you what are the issues with these two techniques. We need to know what are the disadvantages of these two techniques so that we can see why this DMA was introduced. Okay, so let's see the issues, or I can say the disadvantage of these two data transfer techniques, which are programmed IO and interrupt driven IO. Okay, so let me tell you, in both these mechanisms, what happens? Okay, we do data transfer between IO device and main memory. Yes or no? This is what we want to do. We have IO device. There is a IO device. Let's assume, for example, this can be your mouse or keyboard or hard disk. Okay, and there is my main memory. Okay, so this is our main memory. Okay, now what we want to do, we want to do data transfer between these two. Okay, from IO device to main memory, or from main memory to IO device. This is the data transfer that we want to do, correct? Okay, but in these two techniques, one is programmed IO, another is interrupt driven IO. In both these techniques, actually what happens, in both of them, what happens, the actual data transfer is done by the CPU. Okay, so the actual data goes through the CPU, means, see, this is your CPU. Okay, now here there is CPU here. So actual data transfer will be done by the CPU, means the data will go through the CPU. For example, if you want to transfer data from IO device to main memory, then what will happen? First, this data will go to the CPU register. From the IO device, the data will go to the CPU register. And from the CPU register, we will store the data in the main memory. Yes or no? So you can see in both the techniques, whether you study programmed IO or interrupt driven IO, in both the techniques, the actual data transfer from IO device to main memory, that happens through CPU. So first the data will go from IO device to CPU register, and from CPU register to main memory. Okay, or if you want to transfer the data from main memory to IO device, then what will happen? First the data will go from main memory to CPU register. Okay, first we will load the data from main memory to CPU register, and then we will store the data in the IO. Okay, so in both the techniques, this is what happens, that CPU is involved in the actual data transfer. Okay, now you already know that, for example, in the programmed IO, what we do, In the programmed IO, the CPU will continuously check, is the data ready? Yes or no? The CPU will continuously check, is the data ready? Is the data ready? Okay, without doing any useful work. But in the interrupt driven IO, what happens? The CPU will not continuously check, is the data ready? What the CPU will do? The CPU will do some other task, and when the data is ready, then IO device will tell the CPU that yes, data is ready. But remember one thing, in both of them, once the data is ready, okay, in the IO interface, once the data is ready for transfer, then actual data transfer is done through the CPU. Okay, in both the techniques, the data transfer will happen through the CPU. The data will go via CPU. Okay, this is the point. I hope this point is clear. So you can see in both these techniques, whether you study programmed IO or interrupt driven IO. Okay, so whether you take PIO or whether you take interrupt driven IO. So let me write it here: interrupt driven IO. Okay, in both these techniques, remember what happens. For example, this is your IO device, this is your disk, correct? Okay, from the disk, if I want to send the data to the main memory, this is our main memory. If I want to send data between these two, then actually the data will go via CPU. Okay, this is what this diagram is showing you. You can see, if you want to transfer the data from IO device to RAM, then the data will go via CPU. Okay, so this is the point, that CPU is involved in this data transfer. Okay, this is the point. Now, let me know one thing. The CPU, the CPU has what capabilities? Can anyone tell me? CPU has which capabilities? Like I can say CPU can do data transfer, of course, but CPU can do many complex things. Yes or no? See, CPU can do arithmetic operations. Okay, CPU can do arithmetic operations like addition, subtraction, multiplication, division. Okay, many arithmetic operations CPU can do. CPU can do logical operations. Okay, now you can easily see logical operation, for example, shift operation, rotate operation. So many complex operations CPU can perform. Now comparing these complex operations, what do you think about data transfer operation? Is that a complex operation? Please tell me, is that a complex operation? Like if you want to transfer data from one place to another, is that a very complex thing? No, that is not a complex thing. For example, let's assume you are the CPU. CPU is the boss in any company. CPU is the boss. Now, if the boss will do the data transfer, it is not good. Let the boss do complex things. Okay. For example, the boss, what it can do, the boss can think about some strategy. Yes or no? The boss can execute some complex things, but the data transfer can be done by some maybe peon. Yes or no? Agree? So this is the point, that data transfer, this is a very simple operation. If you think about data transfer, this is actually very simple operation which does not need to be done by CPU. Yes or no? CPU does not need to do it. CPU can do some useful work, or I can say some complex work. Okay, this data transfer from one place to another, if you are transferring the data, that is a very simple operation. Okay, all you have to do, from this place you are transferring the data to this place, so for that you don't need to involve CPU. That is a very simple intuition. So this is what I am saying, that in these two techniques, programmed IO and interrupt driven IO, in these two techniques, the data transfer, the actual data transfer will happen via CPU. The CPU will do the data transfer between IO device and main memory, which is not a good thing, because CPU can do some complex work. CPU does not need to do such simple work, that is data transfer. Okay, so now what we do? Now this CPU, tell me in this situation what the CPU will do. If CPU does not want to do data transfer, because it is a very simple operation, from one place to another you just have to transfer the data, then tell me, if the CPU, or I can say if the boss does not want to do it, then what the boss can do? Boss can hire some person. Yes or no? So this data transfer, this simple operation, for this the boss can hire an employee. Okay, this boss can hire an employee to do the simple data transfer. Yes or no? This employee can do the data transfer. Employee can take data from one place to another. Okay, now you can see this employee is called DMA module, or I can say DMA hardware. This is your DMA hardware. Is this clear? This employee is DMA hardware. So this is what I'm saying, that basically what you can do, the CPU does not need to do the data transfer. Okay, you can see the CPU does not need to involve in the data transfer. What can happen? We can hire a new hardware. Okay, we can put a new hardware, that is DMA hardware. This DMA hardware we can put, and using this DMA hardware, what will happen? There will be direct memory access. Means the data transfer will happen directly. Okay, without any involvement of the CPU. You can easily see from the IO device to the main memory. RAM means main memory, and this is your hard drive, that is your IO device. Between IO device and main memory, the you can see the data transfer will happen directly without any involvement of CPU. Okay, so this is the point. So this is what I'm saying, that we use a hardware, that is a DMA controller. We will call it DMA controller, or you can call it DMAC in short, DMA controller. Okay, or we can call it DMA module. We can call it DMA module. Okay, so remember what we do? We attach a new hardware. This DMA controller, remember, this is a new hardware. Actually, you can think that this DMA controller, this is like a processor itself. See, CPU, this CPU has many capabilities. CPU can do arithmetic operations, logical operations, data transfer operations, yes or no, many operations CPU can do. Okay, but remember this DMA controller, this is a hardware. Remember, this DMA controller, this is also a hardware. This is a hardware chip, I can say. Okay, this hardware, let me tell you, this itself is a mini processor. You can consider this as a small processor. This itself is a mini processor. Okay, this itself is a processor, but remember, this is not as powerful as CPU, because remember, CPU can do arithmetic operations, CPU can do logical operations, but this DMA controller cannot do arithmetic and logical operations. This is a processor only for data transfer. Means this only can do data transfer. Okay, is this clear? So remember, for example, using this DMA controller, you cannot add numbers. You cannot do addition, multiplication, rotate, shift. These things you cannot do. Okay, so remember, you can consider this as a mini processor. This DMA controller, this is a hardware, and you can consider that this itself is a mini processor, and this can only do the data transfer. This is a, I can say, specialized processor for data transfer. Is this point clear? Okay, but remember, the CPU can do many things. Using the CPU, you can do a lot of things, but this processor cannot do all the things. This is a specialized, or I can say dedicated processor for only for data transfer. Okay, so this is the point. So you can easily see, if you want to do direct memory access, means if you want to do direct data transfer between IO device and main memory, if you want to do the data transfer, then IO device is attached to DMA controller. What we do, let me tell you. You can easily see here, this IO device, we attach it to DMA controller. So this is the DMA controller, and we attach this device to the DMA controller. It will happen like this. Let me make a diagram. So it is like this. For example, this is your system bus. Okay, and this is your IO device. For example, this can be your disk, or this can be mouse, anything. Okay, now what we do, there is a DMA controller. Basically, this disk we attach to DMA controller, and this DMA controller will communicate with the system bus. Okay, is this clear? So this is the idea. I hope this point is clear. So you can easily see here, to do the direct memory access, IO device is attached to DMA controller. So what is this DMA controller? This is a hardware. Remember, this is a controller. Okay, and what it will do, it will enable, using this DMA controller, what you can do, you can do direct data transfer between IO device and main memory without CPU intervention. So this is the point. In this diagram, you can easily see, this is the diagram of DMA controller. For example, you can see this is the system bus. Okay, and this is your IO device. This is another IO device, that is your display. And this IO device is connected to DMA. This is your DMA controller. Remember, by default, we can also call it DMA only. Okay, this DMA module, sometimes we can also call it DMA only. Okay, or you can call it DMAC, means DMA controller, or you can call it DMA module, but sometimes we can also call it like DMA only. So this DMA, basically, this is a hardware which is to which this device is connected. This IO device is connected to this hardware, and this DMA controller is connected to the system bus. Okay, is this point clear? And you can see what this DMA will do. Using this DMA controller, what we can do, we can do direct data transfer between IO device and main memory. This direct data transfer we can do. We don't have to go through CPU. Okay, the data does not have to go through CPU. The CPU will not have any intervention during this data transfer. Okay, so this is the point. I hope this point is clear. Now let's move on. Now tell me, in this DMA controller, this is a hardware. Inside this DMA controller, what do you think? What registers we need? See, this is the hardware. Like, this is your DMA controller. Okay, this DMA controller will do the data transfer. Ultimately, this DMA controller is responsible for doing the data transfer. So tell me, what things this DMA controller should have? I can say, what registers What registers this DMA controller should have so that it can do the data transfer? Tell me, what data this DMA controller need to store? I am asking which data DMA controller need to store so that you can do the data transfer using DMA controller. Very simple. What we can do? Okay, first we need source address. Yes or no? Do you agree? If you want to do data transfer, then what you need? Definitely you need source address. Do you agree? Also, what you need? You need destination address. Correct. Also, what you need? How much data you need to transfer? Yes or no? So data size, or I can say data count. How much data we need to transfer? So basically, this is the simple point. In the DMA controller, we have many registers. Let me tell you, all of these are registers. For example, we have source address register, we have destination address register, we have data size register. Okay, there is a data count register. Basically, how much data we need to transfer, from where we need to transfer, okay, and to where we need to transfer. And also what we need to tell what is the mode of transfer. Means, do you want to transfer whole data in single operation, okay, or you want to transfer data in chunks, like I can say in pieces. Okay, so basically this is the simple point. This is the simple point, that this DMA controller has some registers. Is this point clear? So let me tell you that these are the important registers. Remember, there can be more registers. Okay, in the DMA, inside the DMA controller, there can be more registers, but these are the important registers that we need to study. Okay, a student is asking, CPU is needed in the transfer. The CPU is not involved in the transfer. The data will not go through the CPU if you are using the DMA. If you are using the DMA controller, then the data between IO device and main memory, the data will not go via CPU. If you remember, in the programmed IO, in the interrupt driven IO, the actual data transfer that happens via CPU. Okay, but in the DMA, remember, the data transfer will not happen via CPU. Okay, DMA is a processor. DMA is yes, DMA is also like a CPU, remember, but DMA is only for data transfer. DMA is also a processor, remember. DMA, that hardware, this DMA hardware, this is also a processor, but this is a, I can say, mini processor. It can only do the data transfer. Okay, it cannot do arithmetic operations, it cannot do logical operations. It is a very simple, very simple processor. This DMA, it is a very simple, I can say, processor which can only do the data transfer. Okay, now let's see inside this DMA controller what are the important registers. So you can easily see, if you want to do data transfer, then definitely you need source address and destination address. So inside this DMA controller, inside this we have source address register and also destination address register. Okay, very simple. What else you need? You need count register, means basically data size register. How much data we want to transfer? Okay, means there is a count register inside this DMA controller that will keep how much data we need to transfer, means how many bytes or how many words we need to transfer. So you can see count register. This register will hold the number of bytes we want to transfer or the number of words we want to transfer. Okay, this will be given in the question whether we want to transfer byte or word. By default it is byte. Okay, is this point clear? So by default it is byte. This is by default, but it will be given to you in the question how much data, uh, basically number of bytes or number of words, that will be given in the question. But remember, basically there is a count register, and this will hold the number of bytes or word that we need to transfer. Is this point clear? Now, whenever you transfer a byte, then what will happen? For example, in this count register, let's assume this is your count register. In this count register, let's assume you have some value. For example, let's assume 1111. Okay, what this value means? This is 31. Do you agree? Okay, let's assume this is your count register, which is 5 bits. So inside this count register, if you have, for example, let's assume 1111, then simply means 31. Okay, it simply means 31 bytes we need to transfer. Okay, is this clear? 31 bytes we need to transfer. We need to transfer. Okay, is this clear? Now, let me tell you that when you transfer a byte, then what will happen? When you transfer a byte, then what will happen? This will decrement. Okay, then this will decrement. When you transfer another byte, this will decrement. So like this. And when it will become zero, what it means? When it will become zero, for example, when it is one, it means one byte we need to transfer. And when you transfer the last byte, this is the last byte. When you transfer the last byte, then what will happen? Then this count register, this content will become zero. Now, zero means There is no byte to transfer. Yes or no? There is no byte to transfer. So in this situation, the data transfer is over. The data transfer is complete. Okay, so you can easily see. So the DMA controller, when you transfer a data, then this value in this count register, this will be decremented. And when this will reach zero, when it will become zero, it simply means DMA transfer is complete. Okay, DMA transfer is complete. And when DMA transfer is complete, then we can generate an interrupt to the CPU. Okay, the DMA controller, it can generate an interrupt to the CPU that, okay, the data transfer is complete. Okay, so this is the simple point. Now, what else you need in the DMA controller? You need a mode register. Okay, this we will discuss after some time, but let me tell you, there is a mode register also. Inside this DMA controller, there is a mode register. This mode register will tell you which mode of DMA transfer we want to use. Okay, for example, do we want to use burst mode or do we want to use cycle stealing mode? Okay, this difference we will see after some time. Actually, what happens when you have burst mode, then whole data will transfer in one go. Okay, burst mode means the whole data, or I can say a block of data will transfer in one go. But in the cycle stealing mode, what happens? You will transfer only one byte or one word. Then you will give the access to the CPU. Then CPU will do something. Then you will transfer one byte or one word. Then again CPU will do something. So like that. Okay, don't worry. After some time we will discuss what is this burst mode, what is this cycle stealing mode. But the point is that whether you want to use burst mode or you want to use cycle stealing mode, for that we have a mode register. Okay, in this mode register you can specify. For example, 0 means cycle stealing mode and 1 means burst mode. So we can specify, remember, we can specify which mode we want to use. We can specify. Okay, so ultimately, let me tell you that inside this DMA controller, tell me what are the important registers. If this is your DMA controller, this is our DMA controller. It is also called DMAC, DMA controller. So tell me, what are the important registers? There are some important registers. These are address registers. Okay, we have address registers. So there is source address register. There is a destination address register. There is a data size register, how much data we want to transfer, or I can say this is your count register, basically number of bytes. Okay, I can simply call it byte count register. This is your byte count register, how many bytes we want to transfer. Okay, and there is a mode register, and there is a mode register. So these are the important registers inside the DMA controller. Remember, DMA controller, this is a mini processor. You can consider that this is like this itself is a processor, but only for data transfer. Okay, so this is also a processor, remember, but only can do data transfer. But only it can do, or only it can do data transfer. It cannot do arithmetic logical operations. Okay, it can only do the data transfer. So remember, this is also a processor. Very simple. I hope this point is clear. So these are the registers inside the DMA controller. You can see source address, destination address, and byte count. How many bytes we want to transfer. Okay, so far everything is clear. Let me know. Now let's see what the DMA working means. What are the steps involved in the DMA working? Okay, so one by one we will see each step. In the gate exam, they can ask you what are the steps in the DMA working. Okay, so let's see one by one. But before that, let's see how these are connected. See, these are the system bus. In the system bus, what you have? You have address bus, data bus, control bus. Yes or no? Now, what happens to this system bus? Main memory is connected, CPU is connected, and you can easily see DMA controller is connected. And remember, this IO device is connected to the DMA controller. We have already seen this IO device. This is attached to DMA controller, and all these components, CPU, main memory, and DMA controller, all these components, they are connected to the system bus. Okay. Now, here, one thing you remember, that this is also a processor. See, this is also a processor, and this is also a processor. Do you agree that there are two processors? Is it possible that simultaneously this system bus can be controlled by both the processors? Is it possible? See, there are two processors. Like I can say it is a big processor. Okay, it can do everything. It can do data transfer. It can do arithmetic operation, logical operation. It can do everything. This is a big processor, and this is a tiny processor, but this is also a processor. Yes or no? This is a big processor. It can do everything, but this is also a processor. DMA controller, this is also a processor. It is a tiny processor, can only do data transfer. Okay. Now, is it possible that at the same time, okay, it is possible at the same time both of them can have control of the system bus? It is not possible. Yes or no? Only one of them can be master of the system bus at a time. Okay, when CPU is the master of this system bus, then DMA controller cannot access the system bus. Okay, it is like this. Let me tell you. When CPU is the master of system bus, means CPU has the control of system bus. CPU can use the system bus. Then remember, this DMA controller is electrically disconnected to the system bus. Let me tell you, it actually happens. This is what happens. Let me tell you that basically when this CPU is in the control of system bus, when CPU is using the system bus, then DMA controller, this is electrically disconnected to the system bus. Okay, means in simple words, this DMA controller cannot use the system bus. And remember, when the DMA controller is accessing the system bus, then CPU is disconnected to the system bus. Okay, is this clear? So this is a simple point. In simple words, I want to say that CPU and DMA controller, only one of them can be bus master at one point at any time. Okay, is this clear? There is a word called bus master. Who is the bus master? So you can see CPU, DMA controller, only one device, only one of them can be bus master at any time. Okay, is this point clear? Let me know. I will discuss all the steps, step by step, how the data transfer will happen using DMA, using direct memory access controller. Okay, so remember, step by step we will see all the things, and these steps are actually important. Okay, so let's see initially what happens, at the end what happens, everything. Let's see step by step. So let's see the first step. The first step is, if the CPU want to do data transfer between IO device and main memory, then remember what the CPU will do now. Let's assume CPU want to do data transfer from disk to main memory. Okay, let's assume. Then what the CPU will do? CPU will send a command to the DMA controller. Okay, CPU will send this command to this DMA controller. Now, what this DMA controller will do? This DMA controller will tell the disk, okay, prepare the data. Is this clear? So the CPU, it will send the command to the DMA controller that I want to transfer data from disk to main memory. And remember, when the CPU will send the command to the DMA controller, then it will also tell, the CPU will tell, remember, the CPU will tell the DMA controller what the source address, what the destination address, and what the count. Okay, how much data we need to transfer, and what the mode, whether it is a burst mode or cycle stealing mode. So all the things will be told by the CPU. So CPU will tell, remember, this is the first step, that CPU want to do data transfer between main memory and IO device. Then what the CPU will do? CPU will send command to the DMA controller, and CPU will tell this DMA controller that what the source address, what the destination address, how many bytes we need to transfer, and what the mode we need to use. Okay, so this information will be given by the CPU to the DMA controller. Okay, is this clear? Then after giving this information to the DMA controller, this is called DMA initialization. Is this clear? The first step, this is called DMA initialization. Okay, and who will do this? This DMA initialization, who will do this? This is done by CPU. Okay, this is done by CPU. So this is the first step, that what the CPU will do? CPU will send this information to the DMA controller, that what is the source address, what is destination address, count, okay, mode, everything. This information will be sent, okay, by the CPU to the DMA controller. So this is called DMA initialization, and this will be done by the CPU. Now after that, what will happen? So after that, CPU will do some work. Okay, is this clear? So once CPU has done this initialization, DMA initialization, then CPU will do some other work. Okay, CPU will do some other useful work. Now what will happen? This device will send the data to the DMA controller, or I can say this device will send the data to the device interface. There is an interface also. Okay, it is like this. It is like this. See, okay, between this device, this is your disk, and this is DMA controller. There is a disk interface also. Okay, there is a disk interface also. So now what will happen? This disk will prepare the data, and it will transfer the data to the disk interface. Okay. When the data will be ready, remember, from the disk, the data will go to the data interface, to the disk interface. Okay. Now, when the data is ready, then This disk interface will tell the DMA controller, okay, that the data is ready. Is this clear? This disk interface, when the data is ready, then it will tell the DMA controller that data is ready. Then what the DMA controller will do? It will send a signal to the CPU that data is now ready for transfer. Okay, so it will send this signal, DMA request signal, or this is also called hold signal. Okay, so either you can call it hold signal, in some computer architecture it is called hold signal, or you can call it DMA request signal. So that is your choice. Now you can easily see the DMA controller, it will send the signal to the CPU that data is now ready for transfer. Now what the CPU will do, let me tell you. Will the CPU immediately give the access to the DMA controller? Remember, right now CPU is using the system bus, correct? Okay, right now CPU is using the system bus. CPU is fetching the instruction, executing the instruction, fetching the instruction, executing the instruction. So CPU is using the system bus. Okay, now when this DMA controller will send the signal to the CPU that okay, data is now ready. Now what the CPU will do? CPU will wait for a DMA breakpoint. Okay, it is not like CPU will immediately give the access. It's not like that. It is not like CPU will immediately give the system bus access to the DMA controller. What the CPU will do? CPU will wait till the next DMA breakpoint comes. There is a concept of breakpoint. Now let me explain what is the breakpoint. You might be thinking, sir, what are the breakpoints? So see, what the CPU is doing? CPU is executing the instruction, correct? Yes, CPU is executing the instruction. So this is your instruction. Let's assume this is the instruction. Now during this instruction execution, what the CPU will do? CPU will fetch the instruction. CPU will decode the instruction. CPU will execute the instruction. If CPU need to access the main memory, CPU will access the main memory, and CPU will write back. Okay, yes or no? So you can easily see that during the instruction execution, these things will happen. Now let me tell you, what are the DMA breakpoints? The DMA breakpoints are these. Means if the CPU is fetching the instruction, then after fetching the instruction, CPU can give the control of system bus to the DMA. Okay, let me tell you, at this point, CPU can give access to the DMA, or at this point, CPU can give access to the DMA, or at this point, CPU can give the access of system bus to the DMA, or at this point, the CPU can give control of the system bus to the DMA, or here. Okay, so this is the point. Is this point clear? So you can see the CPU can give access of system bus to the DMA at these points. Okay, these are called DMA breakpoints. These are called DMA breakpoints. Okay, is this point clear? So this is what I'm saying. You can easily see in this diagram. Let me show you a diagram. So you can see these are the DMA breakpoints. Okay, the CPU can give the control of system bus at these points. Okay, is this clear? So for example, let's assume CPU is decoding. Let's assume CPU is decoding and the DMA request comes. Okay, when CPU is here, for example, let's assume CPU is decoding and the DMA request comes. Okay, now what the CPU will do? CPU will complete the decoding. Remember, at this point, when the decoding is over, at this point, CPU will give the control of system bus to the DMA. Please tell me, did you understand this point? Let me know. These are called DMA breakpoints. Okay. So you can see easily that this CPU, it will give the access of the system bus to the DMA controller at every breakpoint. Okay. At the DMA breakpoint. Okay. Then what the CPU will do? CPU will send the signal to the DMA controller, acknowledgement signal, that okay, I have given the system bus access to you. Now you can be the master of system bus. Okay, what the CPU will do? CPU will relinquish the bus. Means CPU will electrically disconnect itself. CPU will disconnect itself from the bus. Okay, is this clear? Or I can easily say, in easy terms, I can say that CPU will give the control of system bus to the DMA controller. Now DMA is the master of system bus. Is this clear? Now DMA is the master. Now remember, CPU will do some other work, and now DMA is the master. Now what the DMA will do? Now DMA will do the data transfer. Okay, now the DMA will do the data transfer from disk to the main memory. This data transfer DMA will do. Now when the data transfer will be over, once the data transfer will be over, means count will become 0. Okay, there is a count register. When this will become 0, now what the DMA controller will do? DMA controller will make this request signal 0, that now I don't need this system bus control, I don't need. Okay, now the DMA controller will send an interrupt to the CPU. Okay, now when the data transfer is complete, then DMA controller will send an interrupt to the CPU. Okay, so remember, at the end, When the data transfer is complete, then the interrupt signal will come to the CPU. Now CPU, what it will do? Now it will execute a small interrupt service routine. Okay, that yes, the data transfer is complete, and then CPU will do its work. Okay, so tell me, in this entire process, when CPU is involved, can you tell me? In this entire process, when CPU is involved, CPU is involved only in the beginning for DMA initialization? Yes or no? CPU will initialize. So CPU is involved in the beginning. Also, CPU is involved at the end, because at the end, what will happen? When the data transfer is over, then DMA controller will send an interrupt signal to the CPU that DMA, that this complete data transfer is over. Now the CPU, when the interrupt signal will come, then CPU will execute the ISR interrupt service routine, right? Yes or no? So you can easily see CPU is involved only at the beginning, also at the end. But CPU is not involved during the data transfer. If you are doing data transfer, then during the data transfer, CPU is not involved. Please tell me, all these steps, are they clear? Let me know. Here, what are the important points? Let me tell you. The important point is, this CPU will tell the DMA controller what the source address, what the destination address, what the count, what the mode. This information CPU will give to the DMA controller. This is called DMA initialization. Is this clear? This is called DMA initialization. So here CPU is involved, remember. Okay, for DMA initialization, CPU is getting involved. Now remember what the CPU will do. After DMA initialization, CPU will relinquish the bus. CPU will, I can say, CPU will not have the access of the system bus. CPU will leave. CPU will leave the access of the system bus. Now the access of the system bus will go to the DMA controller. Now DMA controller is the master of the system bus. Now CPU cannot use the system bus. Now the master of system bus, that is DMA controller, and CPU will do some its work. Okay. Now the DMA controller will do the data transfer between IO device and main memory. The direct data transfer will happen. Okay, and at the end, when the data transfer is complete, then DMA controller will send an interrupt signal to the CPU, and now the CPU will execute the ISR because interrupt has come. Yes or no? Interrupt has come, so now the CPU will execute the ISR, and then that's it. Then CPU will continue its work. So these are the steps. I hope all these points are clear. And I told you about DMA breakpoints. What are the DMA breakpoints? Here you can easily see. For example, if CPU is executing, let's assume CPU is performing some addition operation. Okay, inside the ALU, let's assume CPU is performing addition operation. Then remember, during this addition operation, let's assume DMA request comes. Okay, DMA sends a request that now I'm ready for data. Now I'm ready for data transfer. Give me access of the system bus. Now remember, CPU will wait. CPU will wait till the completion of execution. Basically, this is this point. This is called these points. Remember, these are the DMA breakpoints. Means at these points, the CPU can give the access of system bus, the control of the system bus to the DMA. So these are called DMA breakpoints. Okay, is this clear? Please tell me. So at these points, the system bus, the control of system bus, CPU can give to the DMA. I hope all these points are clear. Is this clear? Please tell me. Now let's move on. Now let's see all the steps. Here you can read, I've written all the steps in a very detailed way I've written. So let's see the steps involved in the DMA data transfer. When the processor want to transfer data between IO device and main memory, then what the processor will do? Then processor will issue a command to the DMA module. Okay. So remember, the processor will send a command to the DMA controller that I want to do data transfer. And remember, the CPU will also initialize the DMA module by sending the information about source register, about the source address, destination address, and byte count. So you can easily see that this processor, it will issue a command to the DMA controller, and it will initialize the DMA module by sending the following information to the DMA module. What are the information? The CPU will send this information, that what the address of IO device, what the address of main memory, and how much data we need to transfer, means the number of bytes or words that we need to transfer. Okay, so you can see the CPU will write this information in the DMA register, that what the source address, destination address, and byte count. Now after this, what the CPU will do? Now CPU will do some other work. Okay, is this clear? CPU will do some other work. Now what will happen? Now the data will become ready. Yes or no? See, very simple. CPU has sent a signal to the DMA controller. Okay, DMA control. Now CPU has told everything. CPU has told everything. What the address, what the IO address, what the main memory address, okay, what the count. Basically, CPU has told everything. This information CPU has given to the DMA controller. This is the step number one. Now, what the DMA controller will do? It will notify the interface. There is a IO device interface, like this is your IO device. This is your IO device. So there is a IO device interface. There is an interface. Okay, so now remember, now the DMA controller will notify this DMA, this IO interface that yes, now do the data transfer. Okay, now remember, data will be ready because IO device slowly it will send the data to the IO interface. Yes or no? There is a buffer register here that you already know. There is a data register, buffer register. So what this IO device will do? It will transfer the data to this buffer register. So this we call it ready, data being ready. Okay, what we call it? We call it data being ready. Okay, so when the data is ready, means now the data is here. When the data is here, now what will happen? Remember, CPU is already doing some other work. Okay, after the initialization, CPU is already doing some other work. Now what will happen? When the data is ready, then this signal will go to the DMA controller. This interface will send a signal to the DMA controller that data is ready. Now what the DMA controller will do? Okay, this DMA controller will send a signal to the CPU. This is called hold signal, or you can call it DMA request signal. So basically, this is the name of this signal, or you can call it bus request signal. This is called system bus request signal, bus request signal. Okay, is this clear? Now the signal will go to the CPU. What the CPU will do? Tell me. Now what the CPU will do? When the signal will come to the CPU, what the CPU will do? CPU will wait for the breakpoint. Yes or no? Okay, do you agree? CPU will wait for the breakpoint. Let's assume CPU was decoding. Let's assume CPU was in the decoding stage. So at this point, after the decoding is over, at this point, okay, at the DMA breakpoint, what the CPU will do? CPU will relinquish the system bus. CPU will leave the control of the system bus. And CPU will say, and CPU will acknowledge, remember, CPU will acknowledge, CPU will send an acknowledgement signal, DMA acknowledgement signal, or you can call it hold acknowledgement signal. Basically, CPU will send acknowledgement signal to the DMA controller, that now you can become the master of the system bus. Now what will happen? Now this DMA controller will become the master of the system bus, and then what will happen? This DMA controller will do the data transfer from this buffer to the main memory directly. Okay, yes or no? This direct data transfer will happen, and when the data transfer is over, means in the DMA controller, when the count will become zero, then what will happen? Then this DMA controller will send an interrupt signal to the CPU. Here the interrupt signal will come. Remember, here the interrupt signal will go to the CPU, and then CPU will execute the ISR, interrupt service routine, and then this whole process is over. Okay, so this is what I'm saying. You can see step number 2. After initializing the DMA module, the processor can do some other work. Now what will happen? When the IO device is ready for data transfer, when the IO device will be ready, then what will happen? IO device will inform the DMA module. Now what the DMA module will do? Now the DMA module will send us, because now the DMA module need access of the system bus. Yes or no? When the data is ready, then DMA module need the access of the system bus, the control of the system bus, the control of data address and control lines. Okay, so what the DMA module will do? It will send signal, hold signal, or I can say bus request signal, or I can say DMA request signal to the processor. Okay, now when this signal will come, then what the processor will do? The processor will wait for the next breakpoint, for the next DMA breakpoint. Okay, let's assume the CPU is decoding or executing, CPU is in the executing stage. Now when the signal will come from the DMA controller, the bus request signal will come that I need the access of the bus, I need the control of the bus. Then CPU will wait for the DMA breakpoint. These are the breakpoints. So okay, at this breakpoint, what the CPU will do? CPU will relinquish the control of the system bus, and it will send a acknowledgement signal, hold acknowledgement, or I can say DMA acknowledgement signal to the DMA module, indicating that now you can become the master of the system bus. Okay, now the DMA module is the master of the system bus. So what the DMA module will do? The DMA module will transfer the data one word at a time, okay, to or from the main memory, basically without going through the processor. Okay, means when the DMA controller has become the master of the system bus, now what it will do? It will do the direct data transfer between IO device and main memory. This data transfer will happen. Okay, is this clear? One word at a time. one word at a time, the direct data transfer will happen without going through the CPU. Here you have CPU. Okay. Now, at the end, what will happen? See this. Let me tell you some more details about this data transfer. Some more details. Let me tell you. See, now the DMA controller has become the master of the system bus. This DMA controller, what it is now? Now this is the master. Now this is the bus master, master of the system bus. Now what will happen? Let's assume the DMA controller need to transfer data from IO device to main memory. Let's assume, or main memory to IO device. Okay, whatever you want. For example, let's assume we want to do data transfer like this. Okay, from main memory to IO device. Let's assume we want to do data transfer. Then what this DMA controller will do? This DMA controller will do this data transfer. Remember, this is also a processor. We already know that this DMA controller, this itself is a mini processor. This itself is a mini processor. Okay, for data transfer, it can do data transfer. Okay, so remember, and because it is a mini processor, so it can generate the control signal also. For example, if the DMA controller want to transfer the data from main memory to IO device, then what will happen? The DMA controller will send a memory read control signal. It will send a memory read control signal. Okay, is this clear? This DMA controller will send a memory read control signal to the main memory. Okay, and the address also, the DMA controller will send, yes or no? The DMA controller will also send the address, basically the source address, means from where in the main memory, from where you want to read the data. Okay, and then the data will come on the data bus. The data will come on the data bus. So this data is coming on the data bus. The data is coming. Okay, now remember, this DMA controller will send a signal to the IO device also. This signal will be IO write. This is the IO write signal. Now this, okay, now this data will be written in the IO device. Okay, so overall, what I want to say, that DMA controller, this is a mini processor. Remember, when I say mini processor, what it simply means? It simply means this DMA controller can generate all the signals. This can generate, or I can say it will generate basically the control signals like memory read, memory write, IO read, IO write. Okay, so the control signals will be generated. Okay, this will use the system bus to put the address on the system bus. Okay, also the data. So basically these all things will happen, and now DMA is in the control. Okay, the data transfer will happen. Is this point clear? So you can read this here. The DMA will start the transfer of data from main memory to the IO device. What it will do? By putting the address of the first byte, okay, on the address bus, means in the main memory, like this is your main memory. Let's assume from here I want to transfer the data. So the first byte address, the address of the first byte will be put on the address bus, and we will activate the memory read signal. Now we will read from the main memory. Okay, the data will go from main memory to the data bus. Okay, then we will activate this DMA controller. This will activate IO write signal. Okay, then what this DMA controller will do? When one byte has been transferred, remember you have transferred one byte. Now what it will do? It will decrement the count. It will decrement the count. Also, it will increment the address. Yes or no? So very simple. It will decrement the count. It will increment the address pointer, so that you can transfer the next byte. Yes or no? Because we want to transfer the next byte, so we will increment the address pointer and we will decrement the count. Okay, until this process is finished. Now when this process will be finished, then what will happen? So you can see, when the process is finished, when this transfer is finished, then what will happen? This DMA controller will deactivate the hold signal. Okay, on the CPU, it will deactivate the hold signal. Basically it is telling the CPU that now I don't need the access of the system bus. Now what will happen? Remember, at the end, this DMA controller, when the transfer will be over, when the data transfer is over, then DMA controller will send an interrupt signal to the processor. This interrupt signal will go to the processor that data transfer is over. Now the processor will run a interrupt service routine. So you can easily see that processor is involved only at the beginning for DMA initialization, also at the end for interrupt service routine. So only in these two situations, I can say in the beginning, also at the end, CPU is involved. Other than that, during the data transfer, main data transfer, during the data transfer between IO device and main memory, the CPU is not involved. So these are all the steps. You can see the processor is involved at the beginning, also at the end. not during the data transfer. Okay. Now, one more important thing that I want to tell you. Tell me, during this whole situation, from the beginning till the end, how many interrupt signals are generated? Let me know. How many interrupt signals are generated? Tell me. During this whole process, from the beginning till the end, tell me, during the whole process, how many interrupt signals are generated? Only one interrupt signal is generated. Only one. That is at the end of the complete data transfer. When the complete data transfer is over, then DMA controller will generate an interrupt signal to the CPU. Then CPU will run the interrupt service routine. Other than that, there is no interrupt signal. Okay, let me tell you one more thing. Let's assume, see, some important things I am telling you. These are very important because remember, see, all these points you understand. Let's assume that CPU want to do data transfer between IO device and main memory. Okay, this is your CPU. Understand these things very carefully, that this is your IO device or this is your main memory and this is your IO device. Okay, this is your DMA controller. So let's assume this is the DMA controller. Okay, and this IO device is connected to the DMA controller like this. Okay, now you can easily see here there is a system bus. Okay, this is the system bus. Now you can easily see one thing. Let's assume CPU want to do data transfer between IO device and main memory. Then what the CPU will do? CPU will send a signal command to the DMA controller, and CPU what it will do? It will initialize. Tell me, during the initialization, is CPU doing context switch? Please focus here. See, CPU is executing some program. CPU is executing some program. Now let's assume CPU is initializing the DMA controller. Okay, then will there be any context switch? What do you think? Will there be any context switch like in the interrupt driven IO? In the interrupt driven IO, also in the interrupt processing, there is a context switch, yes or no? If you remember. Okay, during the interrupt processing, what happens? The CPU is executing something, and let's assume interrupt comes. Let's assume interrupt comes. Then what the CPU will do? CPU will save this context. CPU will save this context. CPU will run this program, and then CPU will come back and CPU will resume. This is what will happen. There is a context switch. Yes or no? There is a context switch. Okay, there is a context switch. Now, this is what I'm asking, that when the CPU is initializing the DMA controller, okay, when the CPU is initializing the DMA controller, then tell me, basically CPU is saying, okay, what the address register, what is the destination address, and what the count, what the mode. Basically CPU is initializing the DMA controller. Tell me, is there any interrupt here? Basically, will the CPU save this work and then jump here? No, it will not happen. Let me tell you what will happen. CPU does not need to save the context, because remember here there is no context switch. CPU is not executing a new program. Please focus here. See, in the interrupt processing, CPU need to execute ISR, which is a program. Do you agree? CPU need to execute ISR, which is a program. Yes or no? In the interrupt processing, during the interrupt processing, in the previous lecture, we have already seen this. This is what I'm asking, that during the interrupt processing, you already know that ISR, this itself is a program. So CPU is executing some program, and now CPU want to execute this ISR, then definitely you need to save this program so that you can execute this program. So you need to save the information about this program. But remember here, okay, to initialize this DMA controller, okay, here there is CPU is not executing a program. CPU is not executing a new program. Okay, so what the CPU will do? CPU will basically just pause this. CPU will pause. CPU will pause. That's it. Only pause. Nothing else. CPU will pause. Now remember, CPU will not save this work. Please understand. CPU will not save this work. CPU will just pause. Then CPU will do the initialization. Okay. Then when the data will be ready, then this DMA controller will tell the CPU that, okay, please give me the access of the system bus. Now again, what the CPU will do? Again, CPU will just pause. Okay, CPU will pause. CPU will give the access of the system bus to the DMA controller. Remember here, CPU is just pausing. Please understand here. CPU is not saving this and then going somewhere, then coming back and then restoring. CPU is not doing this. CPU is not saving and restoring. No. CPU is just pausing. Okay, means for example, I am doing something, you come to me that okay, you want the access of the system bus, you want the control of the system bus. Then what I will do, I will just pause. I will not save this work, then restore. No, it will not happen like this. I will just pause. I will just I will just disconnect myself from the system bus. From the system bus, I will disconnect myself. Okay. Or I can say I will relinquish the control of the system bus. And I will tell you, I will send you the acknowledgement signal that now you can become the master of the system bus. Okay. So here there is no interrupt here. Remember, okay, there is no saving and restoring, there is no saving, there is no restoring, there is no interrupt, nothing. Now remember, also one more point. For example, this during the instruction execution, for example, instruction fetch, instruction decode, instruction execution, like this. Okay, during this instruction execution, okay, let's assume CPU is decoding, and at this point let's assume see here the hold request has come, the DMA request has come. Okay, let's assume at this point when CPU is decoding, at this point let's assume DMA request has come. Now what the CPU can do, now the CPU will wait for decoding to be over. Okay, when the decoding will be over, at this point, this is called DMA breakpoint. At this point, CPU will relinquish the system bus. CPU will send the acknowledgement to the DMA controller that now you can become the master of the system bus. Okay, here also remember, the CPU is not saving the context, restoring the context. No, CPU is simply pausing. After the decoding is over, then CPU will pause. CPU will disconnect itself from the system bus. CPU will send acknowledgement to the DMA controller that now you can become the master of the system bus. Okay, then CPU will resume. Is this clear? So there is no context switch here. This is what I'm saying. There is no context switch. There is no context switch. When the context switch will happen? At the end, when the complete data transfer is over, then DMA controller will send an interrupt signal to the CPU. And now at the end, the CPU will do the context switch and CPU will run the ISR because interrupt has come. At the end, interrupt will come. And when the interrupt will come, the CPU will execute the ISR, and that's it. Okay, so this is the complete thing. I hope this point is clear. So you can easily see here that when the CPU will give control to the system, when the CPU will give bus control to the DMA, then remember, also when the CPU is initializing the DMA, it is not an interrupt. Okay, please focus here. It is not an interrupt. There is no context switch. There is no context switch. Okay, what the CPU will do? CPU will pause for some time. CPU will pause for some time. Okay, it will initialize the DMA module, and then CPU will resume its work. This is what will happen. Okay, agree? Is this point clear? One more question I want to ask. But before that, you tell me, is everything clear? What are the steps involved in the DMA data transfer? Please tell me, is everything clear from the starting to the end? Can you like can you recall what are the steps? Let me know. Okay, let me quickly mention all the steps. I'm quickly mentioning all the steps. You can see all the steps are written here. This is a screenshot from the NPTEL. So let me tell you all the steps. Okay, see, every step I'm telling you, you can easily see the steps are like this. When the CPU want to do data transfer, then what the CPU will do? CPU will initialize the DMA controller. This is the first step. Do you agree? When the CPU want to do data transfer, then it will initialize the DMA controller. Okay, it will send command to the DMA controller and it will initialize the DMA controller. What this initialization means? Can anyone tell me what this initialization means? This simply means how many bytes to transfer, what are the address, okay, yes or no, what are the source address, what are the destination address, basically these things. So CPU will initialize the DMA controller. Okay, this is the point. Whenever CPU want to do data transfer between IO device and main memory, then CPU will initialize the DMA controller. Here remember, there is no context switch. Please understand, there is no context switch here. Okay, there is no context switch here, there is no interrupt here. Okay, CPU will pause, CPU will initialize the DMA controller, and then CPU will resume its work. Okay, so you can see now CPU is doing some work. Remember, okay, after doing this initialization, now CPU is doing some work. Now what will happen? Now when the IO device is ready, when the IO device is ready, then IO device will send signal to the DMA. Yes or no? So when the IO device is ready, then IO device will send signal to the DMA controller that now I am ready for data transfer. Now the DMA controller will send request signal, bus request signal to the CPU. Okay, now you can see the DMA controller will send the bus request signal, or I can say DMA request signal, or you can say hold signal, or you can say bus request signal to the CPU. Now what the CPU will do? Again, there is no context switch. Again, there is no context switch. The CPU will wait for the next DMA breakpoint, yes or no? If the request DMA request is coming at this point when CPU is decoding, at this point if the DMA request is coming, then CPU will wait for the next DMA breakpoint, yes or no? When this decoding is over, then at this point the CPU can do what it can do. It can relinquish the control of the system bus, and it can send acknowledgement to the DMA controller. Okay, that now you can become the master of the system bus. Now the DMA controller will become the master of the system bus. Now the DMA controller, what it will do, it will transfer the data between IO device and main memory. Direct transfer will happen. At the end, when it is complete, then remember it will deactivate, the DMA controller will deactivate the request signal, and the CPU, what the CPU can do, one more thing in this E. Okay, in this E, one more thing, that when the transfer is complete, then DMA module will send an interrupt signal to the processor. And the processor, what it will do, it will execute the ISR. When the transfer is complete, then interrupt signal will come, CPU will execute the ISR, and then CPU will resume its work. CPU will take the control of the system bus, and CPU will do its work. Okay, so these are the steps. Now one question I want to ask you, tell me one thing. Do you remember in the interrupt processing, and let's assume interrupt comes at this point, then when the interrupt will be serviced, or I can say when the interrupt will be acknowledged? Tell me. Do you remember from the interrupt lecture, from the last lecture? Do you remember that? Do you remember that? Let's assume interrupt has come when CPU is executing, when CPU is decoding. Let's assume. Okay, interrupt has come. Interrupt has come when the CPU is in the decode stage. Tell me when this interrupt will be acknowledged. Let me know. When this interrupt will be acknowledged. Interrupt is acknowledged at the end of the instruction. In the last lecture, we have already seen. In the last lecture, we have already seen that interrupt is acknowledged here. Interrupt cannot be acknowledged in between when the instruction is executing. Yes or no? Here the interrupt is acknowledged. Have you forgotten the last lecture? In the last lecture, I told you that what the CPU will do, CPU will fetch, CPU will execute, and at the end of the instruction execution, the CPU will check for the interrupt. If interrupt is there, then CPU will save this work, CPU will jump to the ISR, CPU will come back, CPU will resume this work. If you remember, I told you that in the last lecture that interrupt is acknowledged at the end of the instruction. Okay, if CPU is executing some instruction, let's assume CPU is executing some instruction and interrupt comes, then remember, first CPU will complete this instruction execution. This instruction execution will complete, and at this point, CPU will acknowledge the interrupt. Okay, is this clear? At this point, after executing the instruction completely, CPU will check for the interrupt. So, did you notice the difference between DMA acknowledgement and interrupt acknowledgement? Please tell me, did you understand the difference? See, DMA can be acknowledged at these points. At these points, DMA can be acknowledged, but interrupt is acknowledged only at this point. At this point, interrupt acknowledged. Okay, at this point, interrupt is acknowledged. Only here. At the end of the instruction. Okay, but remember, the DMA can be acknowledged at these points. Okay, see, is this point clear? For example, two things I'm telling you. Let's assume when the CPU is executing, when CPU is in the ID stage, let's assume a DMA request has come. Okay, please focus. Let's assume a DMA request has come. Also, interrupt request has come. Okay, let's assume interrupt request has come. Now, remember what will happen? The CPU will check this CPU will acknowledge this DMA request here. Okay, at this point, because these are DMA breakpoints. At this point, CPU will give control of system bus to the DMA. But remember, this interrupt will be acknowledged at the end of the instruction only, not in between. So interrupt can come anytime, but interrupt will be acknowledged only at the end. Okay, is this clear? So I can say that this, okay, here, this is the interrupt breakpoint. This is interrupt breakpoint. Means here the interrupt is acknowledged. But DMA can be acknowledged here also, here also, here also, here also, here also. Can anyone tell me why? You might be thinking why. Can anyone tell me what is the reason? I am asking what is the reason that this is the interrupt breakpoint, that interrupt we are acknowledging at the end of the instruction. Okay, but DMA we are acknowledging in between also. Okay, this is what I'm asking. What the reason? Can anyone tell me? That DMA we can acknowledge here, here. See, DMA we can acknowledge here, 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 here. But interrupt we can acknowledge only at the end of the instruction. Can anyone tell me what is the reason? Yes, very good. A student is saying no context switch for DMA. That is why. Very good, very good, excellent. See, this is the reason that when the DMA when the DMA request has come, for example, at this point, let's assume DMA request has come. Now remember, there is no context switch. We don't need to do any context switch. But for interrupt servicing, we need to do context switch. Yes or no? Notice one thing. Let's assume interrupt has come here. When you are in the ID stage, let's assume interrupt has come. Just think about it. Let's assume interrupt has come. Okay, at this point, let's assume interrupt has come. Now, if you service this interrupt here, for example, interrupt has come. Now, if you save this work and then you jump to the ISR, because now you have to jump to the ISR, then what will happen? If interrupt has come here, and let's assume that we acknowledge this interrupt immediately. We don't wait for instruction to execute completely. Let's assume that here immediately we jump to the ISR. Let's assume. Then tell me what is the problem? The problem is we have to save more data. Yes or no? Notice one thing. See, in the middle of the execution of instruction, in the middle of the instruction execution, if you do the context switch, you are doing the context switch. So you will save this information. Then a lot more information you have to save. Yes or no? You have to save what are the intermediate registers. Okay, many. Basically, you have to save the information regarding the decoding. Basically, what I'm saying that if you acknowledge the interrupt in between instruction execution, then when you do the context switch, then a lot more information you have to save. Okay, so this context switch will become very heavy, I can say. It will become very time consuming. You will have to save a lot more information. So that is the reason what we do. We service the interrupt, or I can say we acknowledge the interrupt at the end of the instruction execution. But remember, in the DMA, what happens? If the DMA request has come, now there is no need of context switch. Because there is no context switch, so what we can do, we can just pause. Okay, we can pause. CPU can pause. CPU can give the access of the system bus to the DMA, and CPU can resume. There is no context switch. We don't need to save any data. We don't need to do any context switch. This is the reason. Okay, is this point clear? Please tell me. Is there any doubt? See, so let me write this, because this can be a future gate exam question. In the gate exam, in future, they can ask you this question. So let me tell you that here interrupt is acknowledged. Okay, here at this point, I can say that this is the interrupt. This is the interrupt breakpoint. Okay, here interrupt will be acknowledged. And what is the reason why we cannot acknowledge interrupt in between? So this might be your question, that why DMA can be acknowledged. So this is a question that I'm asking, that why DMA can be acknowledged at during, I can say, why DMA can be acknowledged during instruction execution, but interrupt is acknowledged at the end of the instruction execution. Acknowledged at the end of instruction execution. So what is the answer? The answer is very simple, because in DMA acknowledgement, there is no context switch. Yes or no? In DMA acknowledgement, there is no context switch. There is no context switch. Okay. So this is the point. There is no context switch. But in interrupt acknowledgement, there is context switch. Yes or no? In interrupt acknowledgement, there is context switch. There is a context switch. So this is the point. I hope all these points are clear. Now let's see modes of DMA transfer. What are the different modes of DMA transfer? So let me tell you one by one. The first mode is cycle stealing mode. Okay, the mode of data, the mode of this DMA transfer. The first mode is cycle stealing. Cycle stealing mode. See, this is very interesting cycle stealing mode. Okay, what this mode basically says. Notice one thing, that when the DMA has control of system bus, then can CPU access the main memory? A simple question I'm asking. When the DMA has the control of the system bus, then can CPU access the main memory? Tell me. Then CPU cannot access the main memory, right? Because when the DMA is the bus master, then CPU cannot use the system bus. So CPU cannot access the main memory. But remember what CPU need to do? CPU need to fetch, decode, execute. Yes or no? CPU need to execute instructions. So CPU need to fetch from main memory, then decode, then execute. Okay, then access main memory, then write back. Okay, then again instruction fetch, decode, execute. So these things will keep happening. Yes or no? CPU need to access the main memory. That is the simple point. CPU need to access the main memory. Now tell me, then if DMA is having the control of the system bus, then what the CPU can do? What the CPU can do? Tell me. If DMA has the control of the system bus, then what the CPU can do? So let me tell you here, the CPU will be idle. Do you agree with me that if the DMA has the control of the system bus, then CPU will be idle, because CPU cannot access the system bus, CPU cannot access the main memory, CPU cannot fetch instruction. So CPU will be idle. That is not good. We don't want CPU to be idle. So if CPU is idle, that is not good. We don't want that. Okay, so what are the possibility? Let me tell you the possibility. That is like this. See, very interesting thing is coming. What we can do, what DMA can do like this. See, let's assume that this is instruction fetch, instruction decode, execute, and this is your here main memory access, and there is write back. Tell me, this is your instruction execution. During this instruction execution, at which point main memory is needed? Tell me. During this instruction execution, in which stage main memory is needed? In which stage CPU need to access the main memory? Tell me. CPU need to access the main memory only in this stage, also in this stage. Yes or no? Only in these stages main memory access is needed. Main memory access needed. Main memory access needed. Okay. Do you agree that only in these two stages? Remember, during the instruction execution, only this is the instruction execution. So during the instruction execution, only in these two stages, the main memory access is needed. Okay. Now let's assume that DMA, what it can do? Can DMA use this cycle, and this cycle? Do you agree with me? Can DMA use these cycles? See, very simple. Let's assume DMA request has come at this point. When CPU is in the decoding stage, during this decoding stage, let's assume DMA request has come. Now, if the CPU gives control of the system bus to the DMA here, then tell me, in the next cycle, will CPU be idle? Very simple question I'm asking. Just tell me this point, that let's assume DMA request has come at this point. Okay, or maybe DMA request has come, let's assume, at this point. See, at this point, when you are fetching the instruction, then let's assume DMA request has come. Okay, let's assume DMA request has come. Is this clear? DMA is sending the request at this point. Bus request has come. Now here, tell me what will happen. The CPU will give bus access at this point, yes or no? What the CPU will do? CPU will grant bus access at this point. This is the DMA breakpoint. At this point, what the CPU will do? CPU will grant bus grant. Okay, this bus access will be given to the DMA. Okay. Now you tell me, in the next 2 cycles, will CPU be idle? Now remember, at this point, please understand, at this point, now the system bus access is given to the DMA controller. At this point, the system bus is in the control of DMA controller. Now the CPU cannot access the system bus, CPU cannot access the main memory. But now you tell me, in these two cycles, during this time, DMA is doing the data transfer. During this time, is the CPU idle? Is the CPU idle? No, CPU is not idle, because during this time, CPU does not need to access main memory. CPU can do the decoding, CPU can do the execution. Then CPU need main memory here. Yes or no? Do you agree? So what I'm saying, I'm saying DMA is stealing the cycles. Do you agree? When CPU does not need the cycle, these cycles are stolen by the DMA for data transfer. So it will happen like this, that DMA, it will steal these cycles, and DMA will transfer maybe 1 byte or 2 byte. Okay, maybe 1 byte, 1 word DMA will transfer. Then DMA will again give the access to the CPU. DMA will again give system bus access to the CPU. Then CPU can access the main memory. Okay. Then again, what the DMA can do? Then again, DMA can take the access of the system bus from the CPU. So this is called cycle stealing. Did you understand the meaning of cycle stealing? See, in the cycle stealing mode, basically DMA is stealing some cycles from the CPU when CPU does not need these cycles. When CPU does not need the system bus, okay, DMA is stealing some cycles so that DMA can do the data transfer, and in parallel, CPU can execute some other thing. Okay, basically, when CPU does not need the system bus, those cycles are stolen by the DMA. That is the reason this is called cycle stealing mode. So when the DMA is when DMA is using the system bus, when DMA is doing the data transfer, during this 1 or 2 cycle, remember, the CPU is not idle. CPU is doing some other work. For example, CPU can do the decoding, CPU can execute the operation. Yes or no? So when CPU does not need system bus, these 1 2 cycles are used by the DMA for data transfer. And then what the DMA will do? Then DMA will again give the system bus control to the CPU. Then CPU can again use the system bus. CPU can again access the main memory, and then again DMA will steal a cycle. This is the overall point. Is this point clear? Please tell me. So overall, what I'm saying, see, cycle stealing mode. Here, what happens? The DMA is requesting. Basically, DMA is requesting the system bus only for 1 or 2 cycles, nothing else, not more than that. DMA is requesting the system bus only for 1 or 2 cycles. DMA only want to transfer 1 byte or 1 word. That's it. Nothing more than, not more than that. Okay, DMA, what it will do? It will take the system bus access, the system bus control only for 1 or 2 cycles. It will transfer 1 byte or 1 word. Okay, and you can see probably when CPU is not using the system bus, when CPU is not using the main memory at that time. So this is called cycle stealing, that DMA is stealing some cycles when CPU does not need the system bus. Okay, is this clear? So you can see DMA controller is basically stealing some cycles from the CPU without the CPU knowing it. That is the reason this is called cycle stealing. Okay, is this clear? And then remember, after transferring 1 byte or 1 word in 1 or 2 cycles, the DMA will again give the system bus access to the CPU. Okay, so this is the point. It is like this. Let me create the diagram. It is like this, that CPU has the access. Here, CPU is accessing the main memory. Okay, during this time, CPU accessing main memory. At this time, CPU is accessing main memory. Okay, let's assume at this time also CPU is yellow, means CPU is accessing the main memory. Yellow means CPU is accessing the main memory. CPU accessing main memory. Okay. Now what the DMA can do? DMA can do like this. See what the DMA can do. It will steal 1 cycle. That's it. Here DMA will steal 1 cycle. Okay. Then DMA will transfer 1 byte or 1 word. DMA will transfer, and then again the control will go to the CPU. Then again the control will go to the CPU. Then again CPU will be the master. Here CPU, here CPU, here CPU, here CPU. Then again, what this DMA will do? Again, it will steal a cycle. Again, it will steal a cycle. Okay, so this is the point. That is the reason this is called cycle stealing mode. Is this point clear? Now, one more thing. Don't think that it will always happen that that CPU is executing something, CPU doing some work. See, most of the time, CPU will not be idle. The DMA, what it will do, it will steal some cycle when the CPU does not need the system bus. But sometimes it can also happen that, see, notice one thing here. Notice one thing. Let's assume at this moment, let's assume DMA request has come. Just think about it. Let's assume at this moment DMA request has come. Now tell me when the CPU will give the access. I am saying, let's assume at this moment when CPU is executing the instruction, at this moment tell me if the DMA request has come. Now this is the DMA breakpoint that you already know. This is the DMA breakpoint. So here what the CPU will do? Here CPU will give the access of the system bus to the DMA. But notice one thing. Now the DMA has system bus access. Now the DMA is the bus master. Okay, but remember, now the DMA is using this next cycle. Remember, in the next cycle, DMA is using the system bus for data transfer. But now tell me what CPU is doing. CPU need to access the main memory, so CPU will be idle. Is this clear here? Here the CPU will be idle. Please tell me, is this point clear? Let me know. So please don't think that during the cycle stealing, CPU cannot be idle. No, no, no. CPU can be idle, but most of the time CPU will not be idle. Okay, is this point clear? Did you understand this point? I am saying that in this cycle stealing mode, DMA most probably, please understand here, most probably DMA what it will do, it will steal some cycles when CPU does not need the system bus. But remember, it does not mean that in cycle stealing, CPU will never be idle. No, CPU can be idle. Okay, CPU may be idle. This is what I'm saying. CPU may be idle or CPU may not be idle. Because what can happen? What can happen? These are the different points. You can easily see two situations you can see in the cycle stealing mode. In the cycle stealing mode, you consider two situations. In the cycle stealing mode, you can see, consider two situations here. This is the instruction execution. Okay, this is the instruction execution. So this is IF stage, instruction fetch stage. Then there is instruction decode stage. Then there is execute stage, and then there is main memory access stage, and then there is write back stage. Okay, so you already know these are the DMA breakpoints that you already know. Okay, these are the DMA breakpoints. All of them. This also. So these are the DMA breakpoints. DMA breakpoints. Okay. And let me tell you one more thing. This is called processor cycle. This is called processor cycle. What this is called? This part. Let me write it. This is called processor cycle. This is processor cycle. Okay. Or you can say machine cycle, or this is called processor cycle. Okay. Some people they also call it machine cycle. Okay. So here remember, this is a processor cycle, 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 and this is a processor cycle. Is this point clear? This is a processor cycle. Let me know. So very simple. Now in the cycle stealing mode, remember what happens? In the cycle stealing mode, the DMA will steal cycles. DMA steals some processor cycles. Steals one or two processor cycles. Remember, DMA steals one or two processor cycles. Okay. And transfers one one byte or one word data. Transfer one byte or one word data. Okay, is this clear? And then the DMA will again give the control to the CPU. Okay, so here two conditions, two situations you need to consider. Let's assume the DMA request has come at this point. Okay, so let me write it. Let's assume the DMA request has come at this point. Now what will happen? Let's assume the DMA request came here. DMA request came here. Now you tell me, at this point, if DMA request is coming, then when the DMA will get acknowledgement here, yes or no? Do you agree? So here you can see at this point. Okay, so let me remove it. Okay, so the DMA request has come at this point. Now, at this point, remember what will happen? Here the DMA request will be granted, yes or no? Bus granted to DMA. Okay, so here bus will be granted to the DMA. Now you tell me quickly, in the next two cycles, these are the two cycles. Now tell me, in these two cycles, you tell me what DMA is doing and what CPU is doing. Tell me, in these two cycles, tell me what DMA is doing and what CPU is doing. CPU working. Do you agree? Because CPU is working, because CPU is decoding and executing. CPU does not need system bus. In these two cycles, please focus. In these two cycles, CPU does not need the system bus. So here CPU is working and also DMA is working. Yes or no? Both are working. DMA is also working. CPU is also working. They are parallelly working. Okay, DMA working means what? DMA working simply means, this simply means one byte transferred. One byte transferred. Okay, so this is the point. Now you consider another situation. What is that? Another situation is, let's assume the DMA request came at this point. Okay, let's assume DMA request came here. Oh, sorry, here. Let's assume DMA request came here. Now you tell me, DMA request came here. Now tell me, now what will happen? Here the request will be granted. Do you agree? Here the request will be granted. Here bus will be granted. Okay, here bus will be granted to DMA. Okay, now tell me, when bus is granted to the DMA, in this next cycle, what is happening? Can you tell me? In this next cycle, what is happening? Let me know. So in this cycle, tell me, in this cycle, what CPU is doing? CPU is idle. Yes or no? Here CPU is idle. But remember, DMA working. So CPU can be idle. This is what I'm saying. Okay, CPU can be idle. Here CPU is idle because remember, CPU need to access the main memory. But who has the control of the system bus? DMA has the control of the system bus. So CPU cannot access the main memory. So CPU will be idle and DMA is working. So CPU can be idle. This is what I'm saying. Overall, this is the point. I hope all these points are clear. Okay, so we have seen what is cycle stealing mode. Is this clear? What is the cycle stealing mode? That basically what this DMA is doing, this DMA is stealing one or two cycles, this is stealing, and then it is transferring 1 byte data, and then it is giving, this DMA is giving the control of the system bus to the CPU again. Okay, so this is called cycle stealing mode. In the cycle stealing mode, the DMA will transfer only 1 byte. 1 byte DMA will transfer, then CPU will use the system bus, then again 1 byte DMA will transfer, then again then CPU will use the system bus. So here basically we say that DMA is stealing cycles. Okay, now what is another mode? So this is one mode, that is cycle stealing mode. What is another mode? The another mode is burst mode. The another mode, that is burst mode. See, the burst mode is something like this. In the burst mode, what happens? The another mode, that is burst mode. Burst mode. Okay, in this burst mode, what happens? Let me tell you. The name itself is telling you. In the burst mode, this happens that the DMA controller, when it will get the access of the system bus, then DMA controller will transfer the whole data, or I can say one block of data. Basically, see, when the DMA controller will get access of the system bus, let's assume here DMA is access, here DMA is the bus master. Okay, once the DMA will become bus master, then what the DMA will do? When the DMA will become bus master, then what the DMA will do? DMA will transfer whole data in single go. Is this clear? What the DMA will do? DMA will transfer whole data, transfers whole data, whole data. Okay, or I can say whole data, or I can say whole block in in one go. Okay, is this clear? So here remember, for a very long time, the DMA will take the access of the system bus. So during this time, what the CPU will do? Tell me what the CPU will do. Please focus here. I am saying that for a long time, because the DMA, what it is doing in the burst mode, DMA is transferring the whole data, or I can say whole block in one go. So for a long time, DMA is the bus master. So for this duration, the CPU cannot access the system bus. CPU cannot access the main memory. So tell me what CPU is doing during this burst mode, during this DMA transfer. What CPU is doing? Let me tell you, either CPU is idle or CPU can use the cache memory. There is a cache memory also, yes or no? So remember, it is not necessary that CPU will be idle. It is not necessary. In the burst mode, it is not necessary that CPU will be idle. CPU can use the cache memory. Okay, but remember, when the cache memory does not have the data, required data, then CPU will be idle. So this is what I'm saying, that in the burst mode, for a long time, for a long duration, the DMA will be the bus master. The DMA, what it is doing, when it will become the bus master, it will transfer whole data in one go. Okay, so during this long time, CPU cannot access the system bus, CPU cannot access the main memory. So what the CPU can do? Either CPU will be idle, or CPU can use the cache memory, or what can happen, CPU can use the cache memory for some time and then CPU will be idle. So this is what I am saying, that it is not necessary that CPU will be idle. CPU may be idle, or CPU may be doing some other work, CPU may be using cache memory. Okay, but it is possible that CPU can be idle also. Okay, is this clear? So this is what I'm saying, that in the burst mode, tell me one more thing, from the data transfer point of view, not from the CPU point of view, from the data transfer point of view, which mode is better, cycle stealing mode or burst mode, from the data transfer point of view? Tell me how much data you can transfer quickly. So tell me, from the data transfer point of view, which mode is better? Not from the CPU point of view, from data transfer point of view, which mode is better? Burst mode, definitely, because in the burst mode, what you can do, you can transfer whole data in a single go. Okay, but in the cycle stealing mode, what you have to do? Cycle stealing mode, one byte to transfer, then one byte to transfer, then one byte to transfer. So definitely, from the data transfer point of view, burst mode is better. Okay, so let me write it here, that from the bit, I can say this is the point, that from data transfer point of view, from data transfer point of view, or I can say throughput point of view, from data transfer throughput point of view, which mode is better? Definitely burst mode is better. Okay, in the burst mode, in single go, basically in very quickly you can send the entire data, you can transfer the entire data. But tell me, from the CPU idleness point of view, tell me, from CPU idleness point of view, which mode is better? From CPU idleness point of view, which mode is better? Let me know. Here cycle stealing mode is better, yes or no? Because in the cycle stealing mode, CPU is not idle for a long time. Also also it is also possible that the cycle which is stolen by the DMA, in that cycle maybe CPU can do some other work, yes or no? Maybe in that cycle CPU does not need to access the main memory. So this is what I'm saying, that from CPU idleness point of view, remember, the cycle stealing mode is better. Okay, and in the real life, which mode we use? Tell me, in your processor, in my laptop, which mode do we use? Which of these mode we use? Both of them we use. I told you that CPU will initialize the DMA controller, and CPU will mention which mode to use. Please understand here, CPU will mention which mode to use. I told you that when CPU is initializing, Okay, during the CPU, during the DMA initialization, what happens? This is the DMA. During the DMA initialization, tell me what happens. This is the DMA controller. Okay, so here when the CPU will do the DMA initialization, then what the CPU will mention? Let me know. During this DMA initialization, the CPU will mention the mode. Correct? The CPU will mention the mode, whether to use cycle stealing mode or burst mode. Is this point clear? The CPU will mention the mode, whether cycle stealing mode, whether you can use cycle stealing mode, or whether you can use burst mode. Okay, for example, depending on the situation, depending on the IO device. Okay, let me ask you one question. Let's assume you have a very slow IO device. Let's assume IO device is very slow. Then tell me, let's assume this is a slow IO device. Okay, tell me which mode will be used. There is a slow IO device. You have a slow IO device, very slow IO device. Now tell me, if you have a very slow IO device, then which mode will be used? Then what the CPU will do? See, CPU knows that okay, this is a very slow IO device. For example, maybe mouse. Okay, consider this situation. Maybe this IO device is, for example, mouse, or maybe this is a some other slow device, for example, keyboard. Okay, yes or no? So in this situation, which mode CPU will mention? When the CPU will do the DMA initialization, then CPU will mention which mode? Cycle stealing mode. Yes or no? It is better. It is better cycle stealing mode because IO device is very slow. For example, mouse. Okay, you will press, for example, keyboard. You will press only, let's assume, 5 buttons in 1 second. In 1 second, you will press only 5 buttons. Okay, then of course, cycle stealing mode is better. Yes or no? So this is the point that if you have very slow IO device, then definitely cycle stealing mode is better. And now you tell me, if you have very fast IO device, for example, hard drive. Okay, let's assume you have a fast IO device, fast IO device, and let's assume large chunk of data is coming. Fast and large chunk of data is coming. For example, this is a fast IO device sending large chunk of data, sending large amount of data. For example, your hard drive. Okay, let me give you the analysis. Fast device which sends large amount of data. Example, let me give you the example. Example is your hard drive, your disk. For example, from the hard drive, you are sending, let's assume, movie. Okay, movie can have maybe 500 MB size. Yes or no? So this is the point that let's assume you have a disk which is a fast device. Okay, and it is sending large amount of data. Then tell me which mode is better. Let me know which mode is better now. In this situation, burst mode is better. Yes or no? In this situation, the burst mode, that is better. So this is the point that depending on the IO device, you can use either burst mode or cycle stealing mode. If the IO device is very slow, if the data is coming very slow, you can use the cycle stealing mode. CPU can initialize, CPU can mention that okay, use the cycle stealing mode. And if the IO device is fast, for example, your hard drive, your hard disk, okay, and the data is coming in large chunks, large amount of data is coming, then you can use the burst mode. So remember, both the modes you can use, cycle stealing or burst mode. Both of them you can use, no problem. Depending on the IO device, you can use both of them. Now, on your screen, you have two block diagrams. Tell me which of them is for burst mode and which of them is for cycle stealing. This is a question. Please tell me. Question I am asking that this diagram, which diagram is for cycle stealing mode and which diagram is for burst mode? Tell me. Let me know. The first diagram, see what the first diagram is saying. The first diagram is saying that DMA controller takes over the bus, means the DMA is now the master of the bus. Okay, when the DMA is master of the bus, then DMA will transfer one word, and then DMA will return the bus control, and then DMA will again take the control, then again transfer one word, then again lose the control, basically give up the control of the system bus. Okay, then again, so this mode, what it is called? This is called cycle stealing mode, yes or no? See, DMA is taking control of the bus, transferring one byte or one word, then giving up the control, giving up the control. So this is called cycle stealing mode. The first one, this is the cycle stealing mode. And in the burst mode, what happens? The DMA will take control of the bus and then it will transfer the whole data. See, notice. The DMA will take control of the system bus, then it will transfer whole data, then it will transfer whole data, then it will return the control. That's it. So remember this diagram on your screen. This is the definition of cycle stealing mode. This is the cycle stealing mode. Okay, is this clear? This is the cycle stealing mode of DMA transfer. Of DMA transfer. And this next one, this here you can see the DMA will take control of the bus, then DMA will transfer the data. Okay, the whole data DMA will transfer. The whole data DMA will transfer, and then DMA will give up the control of the bus. So this is called burst mode. This is the burst mode of DMA transfer. So very simple. Tell me the answer for this question. This is GATE 2024 question. GATE 2024. Which of the following statement is false? In the cycle stealing mode of DMA, one word of data is transferred between IO device and main memory in the stolen cycle. Is this correct? Is this statement correct? True or false? In the cycle stealing mode of DMA, one word of data is transferred between IO device and main memory in the stolen cycle. Yes, this statement is actually true. Okay, because in the cycle stealing mode, what happens? Tell me quickly. In the cycle stealing mode, what happens? Very simple. The DMA is stealing the cycles when the CPU does not need the system bus. Then DMA is basically stealing the cycles. Okay, what the DMA will do? DMA will steal one cycle, DMA will transfer one byte or one word of data, then DMA will give the control of system bus again to the CPU. Okay, so this is what your cycle stealing mode means. So very simple. Now tell me one more question. During the cycle stealing mode, the CPU will remain idle or it will never be idle? Tell me. During the cycle stealing mode, the CPU in the stolen cycle, when the DMA has stolen the cycle, okay, one cycle DMA has stolen. Now DMA is transferring one word or one byte. Now during this stolen cycle, the CPU will be working or idle, or what will happen? The CPU may or may not be idle. Yes or no? We have already seen CPU may or may not be idle. Okay, it is possible CPU can be idle. Yes or no? We have already seen in our lecture. We have already seen that it is possible CPU can be idle, but it is also possible CPU is not idle. So CPU may or may not be idle. This is what we have already seen in our lecture, in this lecture. Okay, what about part B? For bulk data transfer, the burst mode of DMA has higher throughput than the cycle stealing mode. Tell me, is this statement true? For bulk data transfer, you want to transfer a large amount of data, then tell me, from the data transfer point of view, you tell me the burst mode is better or cycle stealing mode is better? Which will give you higher throughput? Tell me, which mode is better? Which will give you higher throughput for the data transfer? Definitely burst mode. Yes or no? This is what we have already seen. So this is also true. So remember, these two statements are true. The question is asking false statement, but option A, option B, these are not false statement, these are true statement. Okay, there are two more options that you can easily check in this GATE 2024 question. Okay, tell me the answer for this question. What does CPU do when the DMA is doing the data transfer? What can CPU do, or I can say, what does CPU do during the DMA data transfer? Let me know. Whether you consider cycle stealing mode or whether you consider burst mode, when the DMA is when DMA is in the control of system bus, now tell me, when DMA is doing the data transfer, then tell me what the CPU can do. Let me know. Yes, either CPU can be idle or CPU can be working. But when you say CPU can be working, what it means? See, either CPU can be idle, that is not good. Yes or no? If CPU is idle, that is not good, definitely. Okay, when DMA is transferring the data, when DMA is the bus master, then CPU cannot access the system bus, CPU cannot access the main memory. But what CPU need to do? CPU need to execute instructions. CPU need to fetch instruction, decode instruction, CPU need to execute instruction, yes or no? Fetch instruction, execute instruction, fetch instruction, execute instruction. So CPU need to execute the instructions. Okay. And remember, to execute the instructions, CPU need to access the main memory. But DMA is the bus master. DMA has the control of the system bus. So CPU cannot use the system bus and CPU cannot access the main memory. So during this DMA data transfer, what CPU can do? Yes, very good. Either CPU will be idle, that is one possibility, but that is not a good possibility. We don't want CPU to be idle. Another possibility is CPU can use system bus. CPU can use cache memory. Another possibility is CPU can use cache memory. Yes or no? Is this clear? So remember one more thing. There are many possibilities actually here. In the cycle stealing mode, what CPU can do? When DMA transfer is happening in the cycle stealing mode, when the DMA transfer is happening, then what the CPU can do? Then maybe CPU does not need the main memory in this cycle. Yes or no? In the cycle stealing mode, when the DMA has the control of system bus, then what the CPU can do? Maybe the CPU does not need to access the main memory in this one or two cycle. Okay, so that is one possibility. In the burst mode, what will happen? In the burst mode, when DMA has the control of system bus, then what the CPU can do? Now the CPU can use the cache memory, yes or no? Or the CPU can be idle. CPU can use cache memory or CPU can be idle. So this is what I'm saying, that basically CPU can do some other work. Okay, but remember, CPU can be idle also. You can see CPU might also use the cache. CPU can use the cache memory. Also, you can easily see that if DMA has taken only one or two cycle, let's assume DMA has taken only one or two cycle in the cycle stealing mode. Let's assume DMA has taken one or two cycle. Then maybe CPU does not need main memory in this cycle. Yes or no? It is also possible. Do you agree? It is also possible that CPU does not need to access the main memory in these cycles. Okay, but remember, in the burst mode, CPU can use the cache memory. Okay, this is the point. But remember, CPU can be idle also. If cache memory does not have the required data, the data I want to access, the instruction I want to access, maybe that is not in the cache memory. If that is not in the cache memory, then definitely I have to become idle. CPU will be idle. Okay, is this clear? Now, one more important thing. If CPU is idle, consider this situation, that during the data transfer in the burst mode, let's assume you are transferring large amount of data. Okay, so you are using the burst mode of the DMA transfer. Now, in the DMA transfer burst mode, you tell me CPU is idle. Let's assume CPU is idle. Let's assume. Okay, let's assume CPU is idle. Then, is it still better than interrupt driven IO? Is it still better than DMA? Is it still better than interrupt driven IO? Tell me. Let me know. In the last lecture, we have seen interrupt driven IO. I'm asking, during the DMA data transfer burst mode, okay, when DMA is using the burst mode, DMA is transferring large amount of data in the burst mode. Now, during this time, if the CPU is idle, now this idleness, is this better than interrupt driven IO? The answer is yes. Okay, the DMA, if it is like CPU is idle during the burst mode, okay, when you are transferring large amount of data, then remember, the idle, if CPU is idle, that is still better than interrupt driven IO. Why? What is the reason? Because in the interrupt driven IO, CPU has to do context switch. The context switch is very much time taking. Okay, see, in the DMA, what the CPU will do? Okay, when there is burst mode, then what the CPU will do? CPU will remain idle. Then the burst mode, the data will transfer, and then CPU will again resume the execution. But in the interrupt driven IO, what happens? CPU will do context switching. This context switching takes a lot of time. Okay, is this clear? So that is what I'm saying. Even if CPU is idle, this is the point. Even if CPU is idle during the DMA transfer, still DMA is more efficient than interrupt driven IO. Okay, is this point clear? What I'm saying? I'm saying even if CPU is idle during the DMA transfer, still the DMA is still better than interrupt driven IO. Why? What is the reason? What is the reason? I've written it here. The reason is, in the DMA there is no context switch, but in the interrupt driven IO there are context switches. Okay, so you can see the reason is because, first of all, minimal CPU involvement. When DMA is doing the data transfer, then CPU is not involved. And the second point, that context switch is not there. Because remember, context switch takes a lot of time. Okay, you are saving the program, you are running another program, then you are restoring this program. Context switch takes a lot of time, let me tell you. Okay, like you are saving this program, first you will save this program, then you will run this program, then you will again restore this program. So this context switch actually takes a lot of time. Also, in the interrupt driven IO, the actual data transfer will be done through the CPU. So CPU has to do the actual data transfer. So that is what I'm saying, that DMA is still better than interrupt driven IO. Okay. So this is the point. Now, one important point I want to tell you, if you have small data transfer, okay, if you are having small data transfer, then remember, interrupt driven IO is actually better than DMA. Okay. What I'm saying that if you have small data transfer, let's assume that you have small data transfer. Okay, for example, let's assume you only want to transfer maybe 1 or 2 byte. Okay, let's assume I only want to transfer 1 byte only. Okay, assume you only want to transfer 1 byte only. Now tell me which is better. Now tell me which is better, DMA or interrupt driven IO, which is better? You only want to transfer 1 byte or maybe few bytes, for example, maybe 4 bytes. Okay, so let's assume you want to only transfer 4 bytes, nothing else. So now you tell me which mode is better, DMA or interrupt driven IO? Now here interrupt driven IO is better. Okay, here interrupt driven IO is better. Why? What the reason? Interrupt driven IO, that is actually better here. What is the reason? What is the reason? There will be context switch, but still this is better. Why this is better? First of all, there will be only one context switch. Yes or no? First of all, there will be only one context switch. Okay, and also let me tell you that DMA initialization actually takes a lot of time. Okay, in the DMA, where is the problem? The problem is DMA initialization. This DMA initialization takes a lot of time, more than context switch, more than context switch. Okay, so this is what I'm saying, that this DMA transfer, sorry, DMA initialization actually takes a lot of time. Okay, and if you remember, at the end there is interrupt also. Okay, and at the end there is interrupt also. DMA also has one interrupt. Yes or no? DMA also at the end there is interrupt. Do you agree? At the end there is interrupt. At the end there is one interrupt. So tell me which mode is better. Tell me, if you want to transfer a small amount of data, for example, maybe 4 byte or 10 byte, okay, very small amount of data you want to transfer, then remember, interrupt driven IO is better, because there will be only one context switch, there will be only one interrupt, there will be only one context switch. But the DMA initialization will take a lot of time. The CPU will take the CPU will tell the DMA what the address register, what is the destination register, what is the mode of transfer, what is the word count, everything CPU will tell the DMA. So this is called DMA initialization. DMA initialization will take a lot of time. Also, at the end of the data transfer, when the data transfer is complete, then at the end there will be interrupt signal. DMA will send the interrupt signal to the CPU. So this is what I'm saying, that if you have small data transfer, then interrupt driven IO is actually better. Okay, is this clear? For small data transfer, interrupt driven IO is better. And for large amount of data, the direct memory access DMA is better. So let me write this conclusion. So this is the conclusion. Let me write it here. Conclusion is, if you have large data, okay, you have large data fast device, then which is better? Large data fast device, or I can also say large data small device, then also slow device. Basically, if you have large data, device can be slow, fast, that does not matter. Okay, if you have large data, then DMA better. Okay, then DMA better. Is this clear? And if you have slow device, sorry, if you have small data, if you have small data, then interrupt driven IO is better. Okay, and one more thing. In this large data also, tell me, if you have slow device, then which is better? If you have slow device and you have fast device, if you have slow device, then cycle is telling. then cycle stealing is a good way. Okay, then cycle stealing mode you can use. And if you have a fast device, then burst mode is better. Okay, if you have slow device, then cycle stealing mode is better. And if you have a fast device, then burst mode is better. So this is the final conclusion. I hope you understood. Now let's move on. Tell me the answer for this GATE 2022 question. Which one of the following facilities transfer? Which one of the following facilitates transfer of bulk data? You are transferring bulk data from hard drive to main memory with the highest throughput. Tell me which of them is better? Which transfer technique, which data transfer technique is better for bulk amount of data? So the answer is DMA. Okay, answer is DMA. But remember, if you have small amount of data, then what is better? If you have small amount of data, then what is better? In the same question, if you have small amount of data, in the same question, if I mention the small, if you have a small amount of data, then what is better? Then interrupt driven IO is better. Okay, is this clear? Please tell me. If you have small amount of data, then interrupt driven IO is better. But if you have a large amount of data, then DMA is better. Okay. So we have seen this DMA. The chapter is over. Everything we have seen. What is DMA? What is DMA controller? Every point, everything we have seen. Please tell me, did you understand? Did you understand everything? Let me know. The concept, the mode of DMA, the steps involved in the DMA transfer. Did you understand everything? Let me know. Is there any doubt? Let's solve one question. But before that, let's study this topic. Let's study a topic that is called cache coherence. DMA and cache coherence. I told you one thing, that when DMA is transferring the data, when DMA is in the control of system bus, then CPU, what it can do? CPU can access the cache memory. Yes or no? If the DMA is the bus master, DMA is in the control of system bus, then CPU cannot access the system bus. CPU cannot access the main memory. So during the DMA transfer, what the CPU can do? CPU can access the cache memory, that we already know. Okay. So now you tell me, is there any problem if CPU is accessing the cache memory and DMA is transferring the data between IO device and main memory? Simultaneously, if these two things are happening, then it feels like a good thing. Yes or no? You might be thinking, sir, CPU is accessing the cache memory, so CPU is not idle. CPU is doing some useful work. And DMA is also transferring the data between IO device and main memory. So that is also happening in parallel. Two things are happening in parallel. DMA is also working, CPU is also working. So it is a good thing. Yes or no? Do you agree with me? It is a good thing. Do you agree? Now, is there any problem if these two things happen in parallel? Is there any problem? CPU is accessing the cache memory. In parallel, DMA is transferring the data between IO device and main memory. These two things are happening simultaneously. DMA has the control of the system bus, but still CPU is not idle. CPU can execute the instructions from the cache memory. CPU can access the cache memory. Is there any problem? Do you think is there any problem? Very good. There is a problem. There can be a problem, and that is data can be wrong. Very good. A student is saying data can be wrong. Yes. This is called cache coherence problem. Okay. In the case of DMA, there is this problem, cache 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 coherence problem. You can call it cache memory or you can call it cache memory. Okay. So in the case of DMA, this cache coherence problem can be there. Let me explain this cache coherence problem. It is like this. See, this is your main memory. This is the main memory. Okay. And there is CPU here, and there is CPU here, and there is a cache memory here. Here you have a cache memory. Okay. And there is this IO device which is connected to the DMA. Okay. So there is a DMA here, DMA controller, and there is a IO device. Now, okay. See, a very simple point I'm telling you. I'm telling you two problems. Okay. Two problems I will tell you. See, it is possible that, see, some data, let's assume the data that is here. Okay. In this location, there is some data. Let's assume that data is Y. In this location, there is data Y. Okay, and this data, let's assume, is in the cache memory now. Okay, so when this data is in the cache memory, this data, okay, location y, location, this is L means location. Okay, so let's assume this data is in the cache memory. Okay, now you consider this situation that now DMA has the control of the system bus. What the DMA is doing? DMA is doing the data transfer between IO device and main memory without any intervention of the CPU. And what the CPU is doing? CPU is executing this data. Okay, now you consider this situation that CPU is executing the data from the cache memory. CPU is using the cache memory. But let's assume at this point, what the DMA can do? The DMA from the IO device to main memory, let's assume the data you are sending, and this data has changed. This data, see, okay, this data, let's assume this data X has come now. Okay, so this data has changed now. This X, this Y has become X. But what the CPU is using, what the cache memory has, cache memory still has Y. Yes or no? Cache memory still has the old data. So you can see when this data has become X, okay, when this data has become X, then here notice one thing, then can I say this is old data, or I can say this is stale data? Okay, is this clear? So this is called cache coherence problem. You can easily see CPU is using the cache memory, but you can see if in this location L, if I am writing this data X, this new data, remember this X, this is the new data in location L. In the location L, you are writing the new data. Remember this DMA controller, because remember this DMA controller is doing the data transfer between main memory and IO device. So if this DMA controller is writing this new data in this location L, now this cache memory still has old data. This is called stale data. So this is one problem. Is this clear? So remember this is a case one of this is case one. This is situation one of cache coherence. Did you understand? Let me know. Let me give you another situation. Let me give you another situation. The another situation is like this. Let's assume that CPU has changed this data. Okay, see, CPU is working on the cache memory. Do you agree? Now let's assume in the location L, CPU has changed this data. This Y data, CPU has changed it. CPU has changed it and CPU has made it X. Okay, please focus. CPU has made it X. So now remember, CPU has changed the location, the data in location L. What CPU did? CPU has changed, focus here, CPU has changed data in location L. Right? Agree? Okay, data in location L has been changed. But let's assume DMA has the control of the system bus. Okay, DMA has the control of the system bus, and let's assume this location L data from the main memory, because DMA is doing the data transfer between main memory and IO device. Let's assume DMA is transferring this data here. Let's assume DMA is transferring this data Y. Let's assume this location L data, DMA is transferring here. Okay, then tell me this data Y that DMA is transferring, this is a stale data or not? Let me know. This is a stale data or not? Yes, this is a stale data. Do you agree? Now, here actually one thing you might be thinking, sir, if CPU is writing in the cache memory, then immediately CPU will write in the main memory. Will it happen? If you remember in the cache memory, in the cache memory, there is a concept of write back, write through. Let's assume cache is write back. Let's assume cache is write back. Okay, write back cache. Let's assume cache is write back cache. Okay, what it means? Write back cache, what it means? It means that when the CPU will write data in the cache memory, then immediately the main memory will not change. Immediately it will not happen. Okay, see, in the write back cache, what happens? In the write back cache, if the CPU is writing a new data in the cache, then immediately the main memory will not change. Immediately the main memory copy will not change. So this is what I'm saying. If your cache is write back cache, okay, means when the CPU is writing a new data in the cache memory, immediately the main memory copy is not changing. So main memory has an old copy. Okay, this is a old copy, or I can say this is the stale data. So you can see if the DMA is transferring this location Y data to the IO device, then this is a stale data. So this is the cache coherence problem. Please tell me, did you understand both the situations? So there are two cases of cache coherence. Both of them, did you understand? Let me know. So remember, cache coherence can be solved. There are solutions to cache coherence. You might be thinking, sir, during the DMA transfer, we cannot use cache. Yes or no? You might be thinking, sir, because of cache coherence, during the DMA transfer, the CPU has to remain idle. CPU cannot use the cache memory. No, there are solutions to cache coherence. There are some solutions, but those solutions we will not discuss because that is way beyond gate syllabus. Okay, we will not discuss because those are complicated solutions, and also that is not at all required for the gate exam. In the gate exam, they can ask you about cache coherence. Means when the DMA is transferring the data, DMA has the control of the system bus. Now, if the CPU is accessing the cache memory, is there any problem? Yes, there can be problem. That problem is called cache coherence, cache memory coherence problem. Okay, so this problem I told you. Please tell me, did you understand? Let me know. Did you understand the cache coherence problem? So very easily you can read it here. Okay, so you can see this. This is the cache coherence problem. For example, you can see if the DMA has the control of the system bus. Okay, and let's assume CPU is accessing the cache memory, and let's assume DMA is writing this data. So DMA is changing this data. Remember, this Y is the new value, and DMA has changed this data. Okay, in the main memory, the data has changed, but CPU is using the cache memory, so CPU is using the old data. Okay, so this is the cache coherence problem. There are solutions to the cache coherence problem. Don't worry, there are some solutions. Okay, so that's it. This is your chapter. Please tell me, did you understand? Let me know. Is every doubt clear? Please tell me. DMA, direct memory access. Is this concept clear to everyone? The modes of transfer, there are two modes of transfer: cycle stealing, burst mode. What is the difference between these two? Okay, what are the step by step in the DMA transfer? What are the steps involved? Okay, so every point we have seen. Okay, thank you everyone. In the next session, we will solve each and every gate previous year question of DMA. Okay, so in the next session, we will do a lot of practice of DMA. Many numerical questions also we will solve in the next session. Okay, thank you everyone. This is the complete explanation of DMA. From many standard resources I've compiled this lecture. Basically, in this lecture you will have the complete explanation of DMA. This is the DMA complete lecture. In the gate exam, any question will come, that will definitely come from this lecture, because I've already compiled from many standard resources. I've collected the concept related to the DMA, and this is the complete lecture. Okay, so if you have understood this lecture, if you have understood everything in this lecture, then in the gate exam, any question comes from DMA, you will be able to solve. And remember, in the next lecture, we will do a lot of practice of DMA. We will solve each and every gate PYQ based on DMA. Okay, thank you everyone. Please like this session and please share your feedback in the comments. Okay, thank you.